If you have a workstation or server with NVIDIA GPU and would like to have a full AI-ready stack running with large language model and Open WebUI, all within your own Kubernetes cluster for AI model deployment and testing, then this video is for you. Hello everyone, welcome back to the channel. By end of this video, you will learn how to run a local AI stack with micro-K8s, NVIDIA GPU operator, and Ollama. Let's get started. For GPU acceleration, we need the NVIDIA drivers so Kubernetes can access your GPU hardware. As a step 1, you need to install the NVIDIA drivers for your GPU. To check your GPU PCI address, simply run ls PCI-nn then grep for NVIDIA. In my case, I have a GPU of model RTX 3060. If you are on Ubuntu operating system, you can check the list of drivers by simply running sudo ubuntu drivers devices command. This would list all the available drivers. You can choose the driver which is recommended. In my case, it is NVIDIA driver 580 open. I have already installed the driver, but if you want to install, you can run sudo apt install, then the name of the driver and hit enter. This would go ahead and install the driver. And after rebooting, you can check your GPU with NVIDIA-SMI command. This would list the driver version. In my case, it's 580.95.05 and the CUDA version is 13.0. If you see your GPU listed, like me, it's NVIDIA G4 RTX 3060, then you are ready to move forward. Running a Kubernetes cluster directly on your Linux host gives you bare metal performance for your workloads, direct GPU access without virtualization overhead, and full local control. Let's get Kubernetes running. The easy way is using micro-K8s. Micro-K8s is lightweight, production ready, and maintained by Canonical, the same folks behind Ubuntu. Let's head back to our terminal, and we can install micro-K8s by running sudo snap install micro-K8s. Then we're going to pass --classic --channel is equal to 1.33/stable. Let's hit enter. Let's add our user to the micro-K8s group by running sudo user mod -a capital G, then micro-K8s, then the user. Let's create a .cube directory by running sudo mkdir.cube. Once done, we need to change the permission by running sudo chown, then -f -r, then the user, followed by the directory, which is .cube. Let's create a new group by running then micro-K8s. You can verify the installation status by running micro-K8s status --wait -ready command. To interact with our micro-K8s or the Kubernetes cluster, we need kubectl. Let us head to the official documentation site of Kubernetes and install the kubectl tool by using curl. Let me grab this URL. Go back to our workstation and hit enter. Once downloaded, we're going to install it by moving the executable file to /usr local bin. Let's copy this command, go back and run. This would install kubectl on your workstation. You can just verify by running kubectl command. If you get an output, that means you have kubectl installed properly. We need to enable a couple of add-ons which are required To proceed with the demo, I'm going to use microKTS enable command to enable DNS. Then we're going to enable host path hyphen storage for persistent volumes. And I would install metal-lb so that I can access our services using a load balancer IP. I would run microKTS enable, then the add-on metal-lb. It is requesting me to enter an IP address range. I would use 192.168.1.80 to 192.168.1.90. You can easily find out an IP range by running IPA command and use the interface which is in upstatus. Okay, let us configure kubectl alias by running microKTS config, then the .kube/config. This would allow you to run your kubectl command. For example, we can run kubectl get namespaces, etc. We have enabled an add-on called host path storage, which gives us a default storage class called microKTS host path. We are going to create a custom storage class with the retention policy of retain, which is recommended for running production workload to prevent any data losses. If we go back to the VS Code, I have a storage class.yaml file, which is creating a kind storage class. We're calling it production storage class, and the reclaim policy is set to retain. Let's create this. Once done, you can rerun kubectl get storage class command, and you should see another storage class called production SC. We are going to use Helm 3 to install most of our operators, hence we need to install Helm 3 on our host machine. Let's head to the Helm official documentation site and scroll down. We can install using the following commands. You can verify by running Helm version command. We have Helm version 3.19.2 installed. Run microKTS enable Helm 3. It's time to install NVIDIA GPU operator on our Kubernetes cluster. The NVIDIA GPU operator automates the management of GPU drivers, runtime monitoring inside Kubernetes. It ensures that your nodes are always GPU ready, even after updates or restarts. Let us go to the installation section. As I mentioned earlier, we are going to install the NVIDIA GPU operator using Helm charts. First, let us create the namespace by running kubectl create namespace GPU operator. Once done, we are going to add the NVIDIA Helm repository and update using the following command. It's done. Let us go ahead and download the default values by running helm show command and save it as nvidia-values.yaml. Okay, let me open the values.yaml file. Let's head back to the website. In order to successfully install the GPU operator, we need to specify a couple of changes in the values.yaml file. Let's scroll all the way down. If you are using containerd as your container runtime engine, then you need to add the following lines. In our case, we are using microKTS, hence let me copy the following lines head back to the values.yaml, and in the toolkit section, I'm going to add these lines. Ensure the indentation is correct. Let's save and exit. Once done, let's go ahead and install the GPU operator using the Helm command. Let me run Helm install. I'm going to call this GPU operator, then the chart. We are going to install this in the namespace GPU operator, and we're going to use our custom values.yaml file by mentioning -f. Let's hit enter. Let us check if all the GPU operator pods are running using kubectl get pods -n GPU operator. This would typically take some time to pull the image and install it. Let us exit and check the status again by running the kubectl command. We have all our pods are up and running without any issue. Let us run a simple GPU application to verify if our NVIDIA GPU operator is working as expected. Let's scroll down. We have a sample, a pod. Let's go ahead and run this. It's created a CUDA vector add pod. Let's run kubectl get pods command and -watch. It is completed. We can run kubectl logs, and as expected, all the tests are passed and we are good to proceed further. Finally, it is time to deploy Ollama LLM in our Kubernetes cluster. Ollama lets us run large language models locally and efficiently. We'll deploy it as a containerized service within our microKTS cluster. If we take a look at their official GitHub page, they have listed all the supported models. In our case, we are going to install Mistral. Let's head back to our terminal and create a namespace by running kubectl create namespace Ollama. Once done, we are going to create a persistent volume claim called Ollama. It is going to use a storage class production SE, which we created a while ago. Next, I have created a Ollama deployment.yaml file, which basically have a single replica, which uses the Ollama latest image, and ensure you are mentioning the limit for the GPU set to 1. Also, we are going to create a service of type cluster IP. Let's go ahead and create this deployment and the service and hit enter. Let's go ahead and run kubectl get pods -n Ollama. The container is creating, the container is running. All right, it is running. Let us exit and run kubectl get pods Ollama, and also we can do kubectl get svc -n Ollama. So we have our service. Let us load the model into our Ollama. First, let us go ahead and define a variable to get the pod name. Once done, we simply run the following command to load a model, in our case, Mistral, which is Ollama pull Mistral. It's done. Let us verify the model is loaded by running Ollama list command inside the container, which shows that we have a Mistral latest. Let us test Ollama service by port forwarding our service using kubectl port forward in a terminal. Let us open another terminal and make a simple curl request to our model Mistral to explain a Kubernetes crash loop backoff in one sentence. Let me hit enter. So we got a response which explains a Kubernetes crash loop backoff refers to a state where a pod container repeatedly crashes and restarts. So this is good for testing, but it would be nice if we have a UI where we can just type our prompt and get a response from our AI model. So let's do that by deploying Open WebUI, a lightweight frontend for Ollama. So this is their official web page. So you will get an interface similar to this where you can choose the model and you can start conversing with your local LLM. Let us do that using Helm. So let us go ahead and add their Open WebUI chart by running Helm repo add, then the Open WebUI. Once done, let's run Helm repo update. Let us download the default values by running Helm show values, then Open Web UI slash Open Web UI. Then we're gonna store it to Open Web UI hyphen values.yaml. Let me open the values.yaml file. This comes with the default values. So we need to go ahead and make changes to the Ollama URLs. Let us search Ollama URLs, and this would take a list of values. In our case, we will go ahead and pass our service type, which is http ollama.ollama.svc.cluster.local, and the port number is 11434. Let's save this and exit. Let's go ahead and install by using helm install command. Let's go ahead and check the status of the pods by running kubectl get pods -n, then the namespace, which is Ollama. Let us keep a watch. While the installation in progress, I will also like to show you the best practice. If you are running the Ollama, they recommend you to use an image with the tag Ollama. So we can take a look if we open our WebUI values.yaml file and look for a tag. We currently using the default tag, which is latest. So you can just install a specific tab, maybe like Ollama, which is recommended. Let's head back and check the status. Still, it's in container creating state. Now it is running, and we are waiting for the Open WebUI -0 pod to be up and running. All our pods are up and running. Let us run kubectl get svc -n Ollama. We have Open WebUI, which is currently cluster IP. So let us go ahead and edit the Open WebUI service and change the service type to load balancer. Let us change the service type from cluster IP to load balancer. Let's save and exit. Let's get the service again by running kubectl get svc -n Ollama. We have an external IP assigned to Open WebUI. This is because we have installed MetalLB in the initial stage. Let's copy the external IP, head back to our browser and go ahead and add a new tab, then open the IP. So this has opened our Open WebUI interface. We can click on Get Started. Let us enter our name, mkbn tech. I will add a dummy email called mkbntech at mkbntech.com and set a password. Click on Create Admin Account. So once done, we have successfully logged into our web UI. So you can see what is new in Open WebUI. Let's close this. From here on the top, you should be able to choose your models. In our case, we have a single model called Mistral. If you have multiple models, they will be listed below here. It is pretty fast since it is using our GPU. And as you can see, we don't have any delay and we're able to get the response. This architecture is ideal for developers who want a higher performance and full control of AI without cloud cost. If you found this video helpful, please hit like, subscribe for more AI and Kubernetes tutorials. Thanks for watching. I see you in the next one.